Hello, my name is Karim Muhammad, and our lesson would be a recap on differentiation and the derivatives of trigonometric functions. Previously, we have learned that the derivative of a function f of x is the rate of change of the function at a point of its graph. We draw an xy graph of a function f of x, and at the point x equals a, we draw a tangent. The slope of this tangent is equal to f derivative of a. Algebraically, f derivative of a is equal to the limit of f of a plus h minus f of a over h as h tends to 0, provided for sure that the limit exists. In this graph, we have another function at the points x equal a, x equal b, x equal c. We notice that at x equal b, the right derivative and left derivative are not equal to each other, and hence the derivative doesn't exist at x equal b, although the function is continuous at x equal b. At x equal c, the function is not continuous and the derivative doesn't exist at x equal c. Now we proceed to another interesting stuff, which is the differentiation, the renowned differentiation rules with some proofs. The first one is the most convenient and the simplest of all. D by dx over a times f of x is equal to a f derivative of x, and a is some real number. We let z to be a times f of x, dz over dx or dz by dx is equal to the limit of z of x plus h minus z of x over h as h tends to 0, which is equal to limit a f of x plus h minus f of x over h as h tends to 0. Factoring out the a from these two terms, we get two expressions: a times the limit of f of x plus h minus f of x over h as h tends to 0, which is by definition f derivative of x. So this is equal to a f derivative of x. The second rule is the addition or subtraction. We would prove it for the addition, and the proof for the subtraction case is similar. We let, as before, z to be equal to f of x plus g of x, then dz by dx is equal to limit z of x plus h minus z of x over h as h tends to 0. So this is equal to f of x plus h plus g of x plus h minus f of x minus g of x over h as h tends to 0. And separating, we get f of derivative of x plus g derivative of x. The third rule, the product rule, d by dx of f times g of x is equal to f of x times g derivative of x plus f derivative of x times g of x. We let z to be f of x times g of x, then dz by dx is equal to the limit of z of x plus h minus z of x over h as h tends to 0. This is equal to f of x plus h times g of x plus h minus f of x g of x all over h tends to 0, adding the following term g of x plus h times f of x minus g of x plus h times f of x, and getting these two terms with each other, and then by factoring out the g of x plus h from these two terms, and by factoring out the f of x from these two terms, we have the following. This is equal to g of x, and this is equal to f derivative of x by definition. This is equals to f of x. This is equals to g derivative of x. So we have this product rule. The fourth rule is the reciprocal rule. D by dx of the reciprocal of g of x, provided that g of x is not equal to 0. This is, as we would prove, is equal to negative g derivative of x over g of x squared. So we let z to be 1 over g of x. So dz by dx is equal to limit z of x plus h minus z of x over h tends to 0. So this is equals to 1 over g of x plus h, and this is equals to 1 over g of x. So we manipulate this a bit. The numerator and denominator. So we get the following: g of x minus g of x plus h. And here we have h times g of x plus h times g of x. So separating these two terms, or writing this more explicitly as a product, we have a negative sign over here, and we have the first limit of 1 over g of x plus h tends to 0, and the other limit of g of x plus h minus g of x over h tends to 0, and we have this negative sign here. Then we have 1 over g of x squared. As h tends to 0, the g of x plus h tends to g of x. And this here, this expression is by definition the derivative of g of x. So we have negative derivative g of x over g of x squared. The fifth rule is the division rule. So we would like to evaluate d by dx of f of x over g of x, provided for sure that g of x is not equal to 0. We would depend or use the previous results, namely the product rule and reciprocal rule, to do this one. So the derivative of f of x over g of x, we have written this division as a product, and from the product rule we have the first term f derivative of x times 1 over g of x, plus the second term f of x times derivative of the reciprocal of g of x. And we have previously calculated this one, so we plug it here. We use previous result. So we have f derivative of x over g of x plus f of x times negative g derivative of x over g of x all squared. We multiply by g of x here, so we have g of x here, and we have g of x squared, and we add these to fractions. So we have the final result f derivative of x g of x minus f of x g of x over g of x all squared. Now we would proceed to some results that we would recite without proofs. The most important of all in the business of derivatives, I would say the chain rule. So we have a composition of functions. We have g of x and f of x, and we would like to calculate the derivative of the composition f circle g, f of g of x. So this is equals to f derivative of g of x times g derivative of x. Number 7 is the power rule, and this is a very familiar one. It's very common. So the derivative of x power n is equals to n x power n minus 1. Number 8 is sometimes useful. We have the derivative of f of x all power n. So it's just from number 7 and with the power rule and the chain rule, we have n f of x all power n minus 1, and we have f derivative of x because of the chain rule. Now we proceed to the derivatives of trigonometric functions. We would calculate the derivative of sine of x. So d by dx of sine of x is equals to limit of sine of x plus h minus sine of x over h as h tends to 0. And there is a very useful identity when one is working with trigonometric functions, namely the following one. It's the addition. Sine of a plus b is equal to sine a cosine b plus sine b cosine a. So we do the following decomposition of sine of x plus h. Sine of x plus h is equal to sine x cosine h plus sine h cosine x, and we have minus sine x here, and all of this is divided by h, and we have the limit as h tends to 0. So getting these two terms together, adding them together and separating, we have the following: sine x times cosine h minus 1 plus sine h times cosine x all over h. And we separate like this, and we have here limit of sine x as h tends to 0 times limit cosine h minus 1 over h as h tends to 0, and we have here limit of sine h over h as h tends to 0 times limit cosine x as h tends to 0. For sure we have previously knew the following two important and famous limits. This one, cosine h minus 1 over h as h tends to 0, this tends to 0, so the first term completely cancels out. And the second one, we have sine h over h as h tends to 0, this tends to 1, and so we are left with this one. This is equals to cosine x. So the derivative of sine x is equals to cosine x. And similarly, one can do in a similar manner, or calculate or evaluate the derivative of cosine x, and it's negative sine x, but we wouldn't do it in details. We would proceed to do more interesting ones. We would calculate now the derivative of tan x. So writing the tan x as a quotient of sine x over cosine x, and using the division rule. So we have sine x over cosine x. We will use the division rule in the following format. We have cosine squared x here, and we use this from the division rule. So this is equals to cosine squared x plus sine squared x. So this is equals to 1, and we have cosine squared x. So the derivative is equal to secant squared of x. And calculating the derivative of cotan x is can be done similarly. And the derivative of cotan would be negative cosecant square x. The derivative of sec x would be secant tan x. The derivative of cosecant x would be negative cosecant x cotan x. In the rest of these rules, we can use the division and product rules in order to prove what I have just stipulated. Now we would proceed to a final exercise, a very important one, in which we are asked to find the derivative dy by dx for each of the following four expressions a, b, c, d. A, we have 3 y equals to 3x power 5 plus 4 cotan x. Let's calculate this one. So from the product rule, we have 3 times 5 x power 4, and cotan x, derivative of cotan x is negative cosecant square x. So we have the second term, 4 times negative cosecant square x. So we have the derivative, this result, 15x power 4 minus 4 cosecant square x. This is done. We have number part B, y is equals to 3 secant x minus 5 tan x. The derivative of sec x is secant tan x, and the derivative of tan is secant square x. So we have 3 secant sec x tan x minus 5 secant squared x, and we can factor out the secant sec x from both terms. So we end up with secant x times the 3 tan x minus 5 secant x. Proceeding to this is done. Proceeding to part C, y equals to x cubed cosecant x. We would use the product rule and the derivative of cosecant x and the power rule. So we have 3x squared times cosecant x, and the x cubed times the derivative of cosecant x, which is negative cosecant x cotan x, and that's it. Now proceeding to part D, which is not an easy one, but not very difficult. We would use the division rule. We would like to calculate derivative of 1 minus cotan x over 1 plus cotan x. So from the division rule, we have here in the denominator 1 plus cotan x all squared, and the derivative of 1 minus cotan x is cosecant square x. So we have here 1 plus cotan x times cosecant square x minus the derivative of 1 plus cotan x is negative cosecant square x. So we have here 1 minus cotan x minus cosecant square x. So by factoring out the cosecant square x, we have 1 plus cotan x plus 1 minus cotan x in the numerator. So the negative cotan x cancels with cotan x, and we have in the denominator 1 plus cotan x all squared. So we end up with this result, 2 cosecant square x in the numerator, and in the denominator we have 1 plus cotan x all squared. And that's all, and hopefully most of here is digested and is clear enough, and thank you for listening.